So let's continue to the second part of the lecture. We will see formulation of the clustering problem, measures of similarities between data and clusters. So what do we need when solving the problem of clustering? Assume we have a set of data from where we have no labels, so that means we don't know what actually the data is containing. Imagine the example of pictures of different pieces of rail, and we have the data, but we don't know what's within. So what we are looking for is a method that can tell us about the data, possibly different groups of data that we have. And in this example, we would like the method to tell us if the data belongs to the set of healthy rails, insulated joints, or rail surface defects. And who knows, maybe in the data we find out that there are other interesting sets. So let's assume that we have two functions that will extract features from the images, and they will provide us two real values. So every image will be described by those two features. Of course, in general, we might have much more features, but we use just two for the sake of the representation and for visualizing the clustering techniques. So this is the problem we have. Data that is mapped into a two-dimensional space, two features. Each data point represents then one image. And here then in the clustering problem, we only have samples. We only have the data. And we don't know labels. We don't know if these images are of healthy rails or rails with defects. So those are all question marks. The goal of clustering is then to uncover, to extract knowledge purely from the data. From that extraction of knowledge, we expect then to form groups of or clusters that will comprise similar samples, similar data. If the features are correctly selected, we can expect that data that is near to each other will contain similar properties. So then we can analyze the data we have. Usually clustering it's applied for exploratory purposes. So of course you know where the data is coming from and what can you obtain from it. But the clustering provides you some first indications of the different types of information data that you are collecting. So if you see the data that we have over there, it appears like there are two major groups of data. We can then draw those regions and call them two different clusters, where the data then they're going to belong to one of the clusters, cluster 1 or cluster 2. And when creating the clusters, what we have to define is a criteria. So whether two samples are similar enough to belong to the same clusters, and also whether two different samples from different clusters are sufficiently far away to be considered members of two actual different clusters. So we need to define measures of dissimilarity or similarity. One of the options is to use what is called the cosine. It's a measure then that considers the angle between two vectors. So probably this formula is familiar to you from linear algebra. Consider then in the plot three different points. This is just for explanation purposes. So now first consider then the points x1 and x3, and over there you see that that's the angle between them, so theta 1, 3. we can also calculate the angle between x1 and vector x2, that's called theta 1, 2. Then when seeing those two angles, then well, it appears that the cosine it indicates that both angles are quite similar to each other. So in that sense, to separate those data, then this might not be the right option for measure of similarities. Now, if you consider then a normalization of the data or a different origin for the vectors, then maybe then the cosine similarity then would provide much more information. So you see over there the angle between the points now theta 1, 2 and the angle theta 1, 3 now is sufficiently different from each other. Other way to quantify the dissimilarity between two data points is by using the Euclidean distance. In this case, in the sense of pairwise distance, so distance between two data points. That's just the distance between two vectors. And in the plot over here, then you can see the two clusters, and in red, then it's highlighted, just one for explanation purposes, one data point. In this plot over here, in green lines, is estimated the distance between points. So this is a property that we like very much for data that belongs to the same cluster. That is that the distance between data points is as short as possible. In the next plot, then we can see now the distance from that red sample to members of the other cluster. In that case, the green lines are much larger, and that's actually a good property that we like. The data belonging to other cluster is far away from the original point that we are analyzing. A topic of attention is going to be where we define the boundaries between clusters. That is because the data that it's near those boundaries, they're going to have a distance to members of the other clusters that might be shorter actually than distance of that point to other samples from the same cluster. So we need to define those regions where the boundary, let's say, between cluster will happen. That's going to be of attention then when analyzing the different algorithms. In the literature, you might find also that there are other options to measure dissimilarity. For instance, the L1 or LP norms and L infinity. Those are all different measures of distances that will lead into different characteristics of the analysis. So let's take those two red dots as example. The Euclidean distance is represented by that green line. If we take the L1, also called taxicab or Manhattan distance, could be the sum of those two green lines. LP is somewhere in between L1 and Euclidean distance, and L infinity then captures the maximum distance with respect to all the components of the vector. So what can we say about the measures of similarities? Well, first is that the choice of the distance metric that you select, then it will determine the results of the clustering problem. The other thing is that the clustering methods, they will rely, of course, in this choice, and what is the best metric is usually related to the application, so to the inherent characteristics of the data that you are using. Now, let's try to formalize the problem of clustering. So let's assume that it's given a measure of similarity, and now we need to define the problem of clustering, and we will have the solutions to have two features that we already discussed a bit with the previous examples. First is that the samples that are in the same cluster are to be near to each other. The other characteristic is that the samples from different clusters are expected to be far away from each other. The best solution, the optimal solution to a clustering problem can be given by the definition of a performance function, also called objective function, and in the clustering literature it's also represented as a cost, and I've seen in some examples that they also called distortion cost. We can consider as a cost function, for instance, the sum of distances between points in a cluster. We can also consider the largest distance between points that belong to a cluster, which is a sort of estimation of what is the diameter of the cluster. Also, there are other options like the sum of the distances from points in the clusters to the centroid of the cluster, or a representative sample of the cluster. We will see that example later with k-means. And you can also think of other methods to define the cost function. Let's consider as example of cost function the sum of the distances from points in the cluster to the centroid of the cluster. In this case, the clustering problem will include the notion of distance from a sample to a cluster. We will define the centroid of a cluster as set super C, and this centroid might be a member of the cluster or might be also a point within the cluster. And in this case, for any cluster C, the cost will be defined as the sum of the distances between samples and centroids, considering only the samples that belong to the cluster. So we can see that the concept here graphically. We have two clusters, C1 and C2, and over there we draw two possible centroids for cluster set1 and the other centroid set2. In this image then, the green lines represent the distance between the centroids to all the members from the cluster. And the sum then of the distance will be the sum of all those green lines that you see over there. So you can imagine that when selecting different centroids, or selecting actually different members for the clusters, we will have different values for the cost functions. The centroids, they appear to be related to the clusters. We will see later some methods to calculate them. The number of clusters is also something that will certainly influence the costs. And in general, then we can think of the problem that we want to solve as a function of centroids, clusters, and with clusters I mean the decision of which data samples will belong to which cluster, and the cost will be the sum for all clusters from 1 to k and the distance within clusters and centroids. So I have then for the final part 3 comments about the formalization of the problem of clustering. The first one is that we will see later that some clustering methods that is going to assume that the data point will only belong to one cluster. There are methodologies that they also include the concept of probability of belonging to a cluster, so that each data point will belong to all clusters, but with a different probability. There's also in the field of fuzzy logic that we have fuzzy clusters, where the data points belong to a different cluster with a defined fuzzy number, or what is called also membership degrees. The comment 2 is that because the cost will depend on the number of clusters, that's actually a usual problem that you need to define. When the number of clusters is given, that's easy to define, but for most problems that's a parameter that is unknown. So we will see that some methods, then they will assume that the number of cluster is given. For others, the number of cluster will be a consequence of the parameters you define for the method. A final comment I have is that the centroids are usually defined as the mean value of the data in the cluster, and we will see the reason why. But then when working with other data structures, for instance, if you have news or videos or images, then the average of different images then will be something that will have a difficult interpretation. So in those cases, then you might also consider that the centroid could be selected within the samples belonging to the cluster. In that case, the centroid will be a representative of the cluster, and it's called the exemplar. And in the figures there below, you see in one case the centroid calculated based on the center of gravity of those data points, and in the right we just select one of the members to be the centroid as the most representative data from the cluster. So wonderful. Then we saw the most important concepts of clustering. Now we're gonna look at different methods for clustering. We'll consider 4 families of methods. One is called the centroid clustering, the other the density clustering, other distribution clustering, and the other connectivity clustering. I like very much this classification because it's very intuitive, but you might find in the literature that there are also other ways to analyze the similarities or differences between clustering methods. So let's start with centroid clustering. We define centroids as representative samples of the clusters. In the case of k-means, we will see that the optimal centroid corresponds to the mean value of the data in the cluster. And in this case, then let's assume that the number of clusters is given. There are 2 main steps in this set of clustering methods. The first one is to update centroids. So in the first iteration, we start with some random centroids that you see over there, the red and the blue one. In the next step, step 2, then we assign data to a cluster that is with the nearest centroid. The line that you see over there represents the division of regions from where data points in one region are closer to the red centroid, and the region that is to the right, those all data points belonging there, they're going to be closer to the blue centroid. Then we update the data points to the nearest centroid, so they all change colors. The ones to the left, they are now red, and the data that is to the right, they're going to be of blue color. In the next step, then we get back to step 1 and we update the centroids. And for instance, we use the mean value of the actual clusters. Then in the next step, we repeat again the assigning data to the cluster with the nearest centroid. We define the new regions, and now you see that there are like 3 red points that now they're going to belong now to the blue region. Then this method is iterative, so you repeat step 1 and 2 again and again until there are no changes in the behavior or in the final solution. Here, just to give you a spoiler of the assignment, you will be playing with railway data comprising the 2 features, and then based on the data you will start to define different clusters You see that depending on the number of clusters, you have different centroids. Then based on the distance you select, you're gonna have different regions. And we will see with more details the method of k-means. Let's see now the other family of methods called density clustering. In this case, you will group samples based on how near to each other they are. The more dense the data, then the more likely those regions are going to belong to the same group. In this kind of method, you will need to define the different parameters. One of them could be the minimum distance between points. So let's select this blue dot, and we will have two main steps. The first one is going to be to select a random point that does not belong to the cluster. That will be the blue one. And the next step is to see if other points are within a distance d from that selected sample. Here we select the distance d that it's too short, and then that will lead into 14 different clusters. Basically, each data point will belong to its own cluster. So let's do things differently and let's increase a bit this distance. Then in the step 2, we have to check if there are other points in the distance d. So you're gonna check, okay, are there other data points nearby? And in this case, yes, there are two others. Then they belong to the same clusters. And then you check again for those new points. Again, okay, are there data points nearby us? In this case, then they are not. So yeah, we stop. Then we have defined one cluster, the blue one, and we repeat then step 1 again. So we select a random point that does not belong to a cluster, and then we checked for a distance d whether there are other points nearby. In that case, we have one more point that it's nearby. Then we repeat the steps again, checking and checking with each other, and we have then those four points for the cluster yellow. We repeat the steps again, and then we will find out that we have one more cluster, the red one. And yeah, after 3 iterations, then the method stops. As you can see, the number of clusters results to be a consequence of the distance that we select. Here I have an open question. For the dataset you see over there, which method would fit the best? Yeah, the answer it's difficult. In this case, it seems like the density-based clustering will perform the best. And then, yeah, you see that the actual selection of the method really depends on the problem you are tackling. So here I would like to show you the application of density clustering for the analysis of tram failure events. Over there you see the city of Rotterdam. In the map you see the tram infrastructure of Rotterdam. With red colors you will see locations where you find more wheel sliding events. Those get registered daily, and here you see the aggregated data. From this spatial plot, what we observe is that there are some locations where it's more likely to have the wheel sliding effects. In the left plot you see with black lines the tram infrastructure, and those blue dots are tram failure events. Because of errors in the positioning, the GPS signal is not accurate. then you get failure events outside the tram infrastructure, which is not the case. It's not possible in this case. Well, unless there's a derailment, of course. So there's an inherent problem with the GPS. This also happens in big cities with big buildings. It also can happen in tunnels that you have quite a noisy positioning. So, but then this is the data that you have. Eventually, this could be corrected with other measurements of positioning. But then, yeah, you have to do the best that you can with the data that is available. And in this case, if you see to the right, you can use the density-based clustering to group data that seems to be most related to specific locations of the infrastructure, and then you can consider then the mapping of those clusters into specific locations of the tram infrastructure. Then you can ask for inspections and to see those locations, because for instance, if you see to the right of the plot, there's barely data points over there. So then it appears that then the tram failure events, the wheel sliding events, that are happening then in the locations that are highlighted. From the whole city analysis, there were 4 characteristic locations that concentrate the most problems. Those are the locations that you see over there. The interesting is that then you can after send somebody to check what's going on in those places, because the events, as they are happening at the same locations over and over again, that reflects that the problem is related to the locations related to the infrastructure. Let's see now another family of clustering methods, the distribution clustering. It will calculate the probability of a point to belong to a cluster. That means that all the samples you have, they will belong to all the clusters, but with a different probability. If we consider a centroid, the probability of the centroid to belong to the cluster will be with a very high probability, probably 1 or 0.9. The farther away you are from the centroid, the lower will become the probability. So here you see just an example. When you are near the center of that cluster, the probability is very high. The farther away you are, the lower it gets. Then in red, then you see a similar curve for another cluster. So again, the closer you are to the centroid, the higher the probability that the point will belong to the red cluster. The farther away you are, then the lower the probability. Possible issues that you might have to deal when selecting this type of clustering method. If you have points that are in between of 2 clusters, then you will need to define whether you need or not to know if a point really belongs to one cluster or the other. Also outliers, so points that are far away of clusters, then they won't belong to any cluster with a high probability. So you might wonder if it's just an outlier to take out, or if maybe the number of clusters should be increased. Let's now check the last family of methods, connectivity clustering. In this case, you will start with individual clusters. That is that each point will belong to their own cluster. Then you will find how similar a data point is with respect to the others, and then you will compare the distances with each other till two locations are near, 2 points are near to each other, so you can propose to merge them into one new cluster. Then you start increasing this distance, and then you will start to comprise more and more clusters until then the moment when basically the whole data set will belong to one whole cluster. Let me see, the clusters, then they can also be represented in a dendrogram, and then later we will see more details when analyzing hierarchical clustering. So here another spoiler of the assignment for this week. You will have the data with two features, and to the right you see the dendrogram of when applying hierarchical clustering. In the dendrogram, then in the x-axis you see the data points. In the y-axis you see the distances between those data points. And when you create the dendrograms, then you start merging 2 points together first when you go to the low distance. And then when you start increasing the distance, you start to glue other data points or other clusters together. Then here you enumerate all possibilities, let's say, for aggregating the clusters, and this gives a whole overview of possible clusters going from one cluster till different number of clusters. The number of clusters will be given by the threshold that you defined based on the y-axis or the distance. So for instance, if you select the threshold equals to 2, you will see that there are 3 lines that are intersecting that level. That means you have 3 different clusters. So finally, the idea of this section was to provide you some general overview of possible methods. Because of this corresponds to only one lecture, then it's difficult to cover all other possibilities and all other methods. So I think then it's this provides you the first overview of clustering. As final comment, then first is that the best method that for clustering will depend on the type of data you have, the inherent characteristics of the data, and the results will be given by how you tune the algorithms, so the tuning parameters. Other aspects that you will need to consider when selecting the method is the scalability of the method. There are some methods that are better fit for low scale data, so for a few hundred data points, but when you're considering a very large scale of data, then probably the dendrogram will be very difficult to analyze, especially if you are dealing with a high number of feature space. The third comment is that if you know the metric that better fit the data, or if you know the required number of clusters that you needed, then that will limit the options for methods. So that's always good if possible to know about that in advance. But usually, as we discussed before, number of clusters it's almost never given. Then finally, you will be using this library to run the test for the assignment. But also, if you go to this web page, you will see a very nice overview of methods. And then they compare them based on the parameters that they have, scalability, use case, and the metric that they use. So this is highly recommended that you play with this.